And what I'm going to do today is complete what I was doing on Wednesday last week, and then move on to the discussion of the propagation of gravitational waves through the real universe. And that's what I'll deal with today and on Wednesday. By that, what I mean by that is propagation of the waves through a universe that is curved due to the large-scale curvature of the universe. A universe that has lumps in the forms of stars and galaxies, so you have interaction with the curvature of space-time associated with those lumps, and through a universe in which there may be matter, and so you have scattering, which we will find is extremely small, of gravitational waves by matter. You have dispersion, that is slowing down of the waves, just like electromagnetic waves slow down when they propagate through glass. But we'll find that that's extremely small. But do we want to understand these standard issues that you meet for electromagnetic waves and see what aspects of them are important and what aspects of them are not important? We will see that for gravitational waves, as for electromagnetic waves, all the interactions with background curvature of space-time are the same. You get gravitational lensing, you get gravitational redshifts, for example. But we will see that interactions with matter are so weak that they can be ignored for all practical purposes, except when you're doing data analysis with a gravity wave detector. Okay, so I had derived in the last lecture a formula for the gravitational wave field, HJK transverse traceless, that is produced by some source in here, which has some stress energy tensor, and we are looking at the waves out here at some distant location, location x at time t, in some background flat space-time. So these are waves that are being produced that are very weak. The energy and momentum are very weak inside this source. So we're just trying to deal with the simplest case. And so I've introduced global Lorentz frame of the background space-time. This is the location of the where the observation is made. There's some location down in here, x prime, at which the source is emitting, and t prime is some emission time. So this, in the language you normally use for electromagnetic theory, would be the source point. That's the field point. And the formula that we derive says that HJK transverse traceless can be computed as follows. You take an integral over the source, so you're integrating over x prime, the source point, of the stress TJK evaluated at the source point, but not evaluated at the time t here, but rather evaluated at the retarded time, just as in electromagnetic theory. So the retarded time is at t prime equal t minus the distance between the 2 points, which is the x minus x prime absolute value. So all this says here is you're evaluating it at the retarded time. Let me just put RET. And then you divide by the distance to the source, x minus x prime, and you integrate over the source point. And then there's a factor of 4 out in front, which has to do with the 16 pi that appears in Einstein's equations when we write it in the way I did, versus 4 pi in the electromagnetic case. But you're not quite finished, because the gravitational wave field we want is transverse and traceless. That is, it has purely components that are in the plane orthogonal to the direction of the source, and in that plane it's trace-free. And this thing is not. And so what you're asked to do then is to project out the transverse traceless part. You just throw away the longitudinal part, and you remove the trace on the transverse part in the manner that I talked about last week. So this is a fancy formal formula for the gravitational wave field from a source under these circumstances. Now, I'd like to motivate changing to a different version of the formula, which is basically equivalent to this. I want to motivate it by looking at a specific example. The example I want to look at is where this source is two masses. Let me put them here and here, that are connected by a rigid rod, well, as rigid as it can be, given that it's made of real materials, so it stretches then. This is a mass M1, or M, and this is an identical mass M. And this is spinning with an angular velocity omega around the center of the rod. The rod I'm going to take to have a cross-sectional area, A, which is going to be important in the discussion. And so for that particular source, I want to look at what is the stress tensor, the components of the stress tensor. Well, there is a piece of the stress tensor associated with these masses, but also a piece associated with the rod. So the contribution from the masses, we can deduce as follows. The stress tensor, in fact, in general, for some material that is moving with some velocity, there's a TJK that will be the density times the velocity times the velocity. So that would be familiar to many of you. Others who have not thought much about stresses for nearly Newtonian systems, this is a nearly Newtonian system, will note that when we talked about the stress-energy tensor for a perfect fluid, and this is in your reading, I've not discussed it in the lectures, but in the reading you've seen about the stress-energy tensor of the perfect fluid. For a perfect fluid, so this is a little side remark, T mu nu was rho plus P u mu u nu plus P g mu nu. And so TJK is rho plus P, Uj UK is just the ordinary velocity at low velocities. That's the components of the spatial components of the four velocity, and that's just the ordinary velocity. So that's what's coming from here, plus a P times a delta JK. Now, inside this mass, the dominant contribution is rho, because this is a nearly Newtonian object, and pressures are very small compared to mass densities for a very Newtonian object. And so these pressure terms, or this pressure term is unimportant, but rho times velocities is of the same magnitude as pressures, typically. However, I'm assuming that this object is a mass that has negligible self-gravity, so there's no reason it should have any significant pressure in its interior. And so I'm going to throw that away. And I just have TJK as rho Vj Vk. So that's the low velocity limit under a circumstance where there's not any significant pressure inside here. So that's what I have for this mass. And if I integrate that, you notice here there's an integral over space. It's divided by x minus x prime, but I just want to look at the magnitude of the contributions roughly. And so if what I'm going to look at is the magnitude of the integral of t over space, not worry about this x minus x prime in the denominator. I just want to see how big that is. So if I do the integral of tjk over space for this mass, the integral of tjk d3x is going to be, well, all of the mass is moving with essentially the same velocity, and the integral of rho over space is just the mass itself. And so I get m, and then the velocity with which it's moving is the angular velocity times the half length of the rod, so it's omega L, and I have two velocities, so it's m omega L squared. So that's the magnitude of the integral of the stress tensor over this mass. Now let's look at the contribution inside the rod. I'll do this in orange. So in the rod, there in fact is a stress, because there's a centrifugal force as this rod rotates. And that centrifugal force means that the rod is stressed by being pulled at the ends because these masses are trying to fly apart. And the magnitude of that stress is Txx along the x direction is equal to the force in the rod divided by the cross-sectional area. This is the force that is required to hold these masses in, given that they're trying to fly apart. And that force in the rod is just a mass times the acceleration that this mass is undergoing to keep it in circular orbit instead of moving linearly. So that's m times L times omega squared. That's the net force that is required to keep this mass moving in circular motion, divided by the cross-sectional area. And so the integral of Txx for the rod's contribution is going to be Txx m L omega squared over the cross-sectional area A, multiplied by the volume of this rod, which is 2 times A times L. That's the total volume of the rod. And so the A's cancel, and I get 2mL omega squared. So you see that the total contribution of this integral from the rod is the same in magnitude as the contribution from the mass. That means if we want to evaluate this formula to compute the gravitational wave field, in this simple case where I have some big masses and a little rod connecting them, and the rod's rotating, it's not just the masses that are going to radiate. The rod's going to emit just as much radiation as the masses, which is a sort of uncomfortable thing to deal with, because that means if you want to compute the gravitational waves, you've really got to deal with delicate things like the internal distribution of the stresses inside your source, and not just worry about the masses and their motion. So what I want to do is manipulate this formula for the gravitational waves into a form where no longer, in this new way of writing them, no longer will the rod contribute. The radiation will entirely come from these heavy masses and their motion. But the answer will be the same as the answer that I would get using that formula.
So what you're talking about is that the stress, the gravitational waves that come from the stress in the rod, from the stress in the massless rod, will contribute, will be roughly equal to the gravitational waves that come from the masses.
According to this formula, the gravitational waves that come from a, quote, massless rod, a rod that has as small a mass as it could possibly have in order to support the, in order to hold these masses together. Gravitational waves from that rod will be just as big as the gravitational waves from these masses. That's the statement. Which leaves one in an uncomfortable situation when you want to do practical calculations, because you've really got to worry about the details of the internal stress distribution in a complicated system. Okay, so I want to manipulate this formula into a form that will be easier to apply in practical situations. As you'll see on this week after the Wednesday lecture, I'll give you a problem set that has a number of practical calculations. Thus far, you've mostly gotten formalism, but we now have enough formalism in front of us that we can begin to do some practical calculations, and you get a real feeling for how things behave in the real world. So I want to manipulate this, and the key thing that I want to do in this manipulation is to assume for my source that it has slow motion. slow motion means that the velocities inside the source are small compared to the speed of light. But that means correspondingly that if you just think it through, that the wavelength of the emitted gravitational waves is going to be very big compared to the size of the source, because because the velocity is basically the size of the source divided by the period of the gravitational waves, which is the same as the size of the source divided by the wavelength of the gravitational wave, since the speed of light is equal to unity. Whereas C is and C is equal to 1, and so the statement is that L over lambda is small compared to 1, or lambda is large compared to L. Okay. So slow motion means speeds inside the source are small compared to the speed of light. It means the wavelength of the gravitational waves is large compared to the size of the source. It means then that the source resides deep inside its near zone, in the language that you use in electromagnetic theory. And this slow motion approximation enables one to get out much simpler formulas than if you're allowing for fast motion. The formula that we have up here made no slow motion approximation, and that's why the retardation is done in this careful manner. We derived it directly from the wave equation using the usual Green's function that you would use in electromagnetic theory, and there was no slow motion approximation went into it at all. But as soon as I make a slow motion approximation, that means that for x minus x prime is essentially the same as the distance between the center of the source and x. That is, x is way out in the field point, way out in the radiation field. So it's at a distance large compared to a wavelength away. And the source is small compared to a wavelength. And so the distance from here to any point in the source is very nearly the same, since the source is small compared to a wavelength, and this distance is big compared to a wavelength. So I can approximate x minus x prime as being essentially the distance r to the center of the source. So let me put that up here. I have center of the source, or I would typically take the center of mass, and that distance to the center is r. I also have the fact that because the waves change very little as light propagates across the source, since the source is small compared to a wavelength, that means that when I write down TJK at the retarded time, I can just retard myself to the center of mass instead of carefully retarding myself to this location, to the source point. I can just retard myself to the center of mass. And so I can approximate then, in the retardation integral, I can approximate T prime equal T minus x prime as being T minus R. In addition, because now the denominator is just r, it's a constant, it can be pulled out of the side of the integral. So I wind up with a formula HJK transverse traceless is obtained by computing 4 divided by r, pulling that outside the integral. An integral then of the stress tensor TJK evaluated at x prime and at t prime equal to t minus r, d3x prime. Now I can just, And then I have to project out the transverse traceless part to get the gravitational wave field. Next, I'm going to use the law of energy momentum conservation, T mu nu comma nu equals 0. I'm doing this in the global Lorentz frame with a background, and I'm going to do this with a comma, which means that I'm ignoring any self-gravity of the source. I'm able, in this discussion, and I said this on Wednesday when I began the discussion, I'm really only able to discuss by the techniques that I have been using the gravitational waves emitted by an object that has negligible internal gravity. That's also a motivation for having ignored these pressure terms up here when I wrote down the stress tensor for the mass. If the mass had significant internal gravity, then it would have significant internal pressure, and I'd have to be concerned about that. Pardon?
What is significant?
Significant means that strong enough to influence the motion of the system. So that is the thing that is, so what I'm saying is that the thing that prevents these particles or these masses from flying apart is material stress, not gravitational forces. Or another way to say it is that if you think about, so that's a way to say it, that the force between these objects is a material force, that is this force that I write down is the TJK, that is rho VJ VK. Let me start over again. I'm not saying that right. The force between the objects is the material force that I have inside this rod, which is the material force that I analyzed here. And it's not the gravitational force between the objects. If it were a gravitational force, then when I write down the law of energy and momentum conservation, I would have to include gravitational contributions. So I would have connection coefficients if I do this in general relativity language. And so that would be a covariant derivative or a gradient in curved space-time. And I'm not allowing for that. Okay.
If the force that pulls the masses together would be gravitational force, then the stress energy tensor in the rod would be zero.
Well, if the force pulling them together was purely gravitational, the stress energy in the rod would be zero. In general, you'll have some mixture of gravitational and material. And in a realistic source, you have some mixture.
Yeah, if it would be only gravitational,
if it were only gravitational, then this would be zero, and this entire discussion would fail. I have built a discussion where it is assumed that all the internal forces are material forces and are not gravitational. Okay, so because of that, I can use the law of energy and momentum conservation that I would have in special relativity to discuss the source. And taking mu equal to 0, this says t00, 0 plus t0j, j vanishes. That's the law of energy conservation because the free index is a 0, and so we're talking about energy conservation. Again, I'm appealing to your having read about the stress energy tensor or already knowing this piece of special relativity. Tj0, 0 plus tjk, k equals 0 is the law of momentum conservation. I'm now going to write down a formula which you can derive directly from the law of energy conservation, the law of momentum conservation, just doing algebra. The formula is a little bit long, but it is the thing that I need to get where I want to go. This formula says the following. It says that t00, 0, so this is something that I would get by taking another time derivative on energy conservation, and then I would have t0j, j0. And then I'm going to multiply it by xj, xk. Remember, I'm in a Lorentz frame, global Lorentz frame, so spatial indices can be up or down. It doesn't matter. This is equal to TLM, ML, xj, xk. That you can get very quickly. You just differentiate this first guy with respect to time, and then you get a 0j, j0, and then you use this relationship, and then you just multiply both sides by xj, xk. So that's a small enough step you can pretty much do it in your head. And then the right-hand side, I claim, is equivalent to the following expression. It's T Lm xj xk comma Lm. So all I do is I pull these derivatives outside of the entire expression. Having done that, I have to put in the corrections that I get from differentiating these x's. And those corrections that I then have to put in turn out to be minus 2 TLJ xk plus TJL x, I'm sorry, TLJXK plus TLK xj comma L. So that's one correction. And then I have plus TJK. Okay, so that's a bit of algebra that you can also almost do in your head and see that, that if I were to take this and differentiate it, I get these three terms from doing those derivatives. This is a sort of a trick that is worth being aware of, that you can get from something that involves just a tjk to something that involves a t00 with two time derivatives times xjxk in this manner. And the other pieces are pieces, this piece and this piece are pieces that in fact are divergences. This is a divergence on the indices L and M. This is a divergence on the index L. So that means that if I integrate the left-hand side over the source, then on the right-hand side, this term integrated over the source will give 0 because it's a perfect divergence. And you use Gauss's theorem to evaluate the integral, and you'll get 0. And this guy will give 0, and all you have left is that guy. So the statement is that when self-gravity is unimportant, then T00, comma 00 times xj xk integrated over the source is equal to the integral over the source of tjk. So I can put that back in here. What I have is just tjk integrated over the source at the retarded time, so there are primes in there. And I can convert that over to this. And so I can say that hjk transverse traceless can be obtained by integrating over the source. Well, I have a 4 over r outside the integral. And then I have a, let me just move this integral over, as you'll see why in a minute. T00, comma 00, xj, xk, let me call it xj prime, xk prime, d3x prime. And this is evaluated at the retarded time. That is at time, let me put the retardation down here. That is, it's evaluated at time t prime equal to t minus r. And we're then to project out the transverse traceless piece. But xj and xk have nothing to do with time. They're independent variables. And so these time derivatives can just be pulled outside the integral. Okay. So I'm going to get rid of them, pull them outside the integral. And let me do that in yellow. And I have d squared dt squared of the integral of the energy density, well, the mass energy density, a couple of x's, spatial coordinates, and then integrated. Go over here to the side and let me just remark that the integral of t00, xj, xk, d3x is often just called the second moment of the mass distribution, where T00 is the total mass energy density relativistically, but in a nearly Newtonian situation, it would just be rho, it would just be the ordinary mass density. So this is the second moment of the source's mass distribution. And I generally use the notation ijk for that second moment. Let me also note that this is related to the mass quadrupole moment. You just remove the trace from this, and then you get the mass quadrupole moment. So the mass quadrupole moment, ijk, which is the mass quadrupole moment, is just the integral of t00 xj xk minus 1/3 r squared d3x. Then r squared times delta jk. This is just pulling off the trace, making it trace-free. Okay. So the second moment of the mass distribution differs from the quadrupole moment just by the fact that the quadrupole moment is the same as the second moment, but with a trace removed. If you convert this over to spherical polar coordinates, you'll recognize this aside from some multiplicative factors just involving a spherical harmonic of order 2. If you convert from Cartesian coordinates to spherical coordinates. And so again, you thereby see that you're really talking about a quadrupole moment. This is a quadrupole moment as discussed in Cartesian coordinates rather than spherical coordinates. Okay. So another way to write this is that hjk, transverse traceless, is just equal to 4 over r, then take 2 time derivatives of the second moment of the mass distribution. You've got to evaluate that at the retarded time, and then you project out the transverse traceless part. Now, because in the end we're projecting out the transverse traceless part, the trace of I doesn't contribute to this formula in the end. If you think it's true, if you were to put in the contribution that comes from the trace, so it would be a piece that would go as a scalar times a delta jk. That's the trace piece. And so in terms of indices, this would just be something times delta jk. You pull out the transverse traceless part of the Kronecker delta, and it's 0. The trace, the fact that you're picking out a trace-free part, that's the only thing that contributes to the gravitational waves, means then that the trace of this does not contribute at all. And so equally well, if it's more convenient to do so, or if it makes you feel better for some reason, you can write this as 4 over r times the second time derivative of the quadrupole moment, evaluated at the retarded time. Take the transverse traceless part. So either formula gives the same result. And what we normally do is say, well, this is the quadrupole moment formula for the gravitational waves, and we think about it in terms of this quadrupole moment being the thing that generates the gravitational waves. But in fact, in a practical calculation, it's just easier usually to use the second moment of the mass distribution in a practical calculation. Now, you recall back when I did the overview of the class, when I using a PowerPoint presentation, we did dimensional analysis and arguments about fields, the radiation fields falling off as 1 over r and being expanded in multiple moments. And from that argument, we got out that the gravitational wave field should look like, the first term we argued should be a mass quadrupole moment, let me call it Q2, with 2 time derivatives divided by r. And then you would have a mass octupole moment, Q3, with 3 time derivatives on it divided by r, and so forth. And we decided that this should be the dominant term, something that would be mass quadrupole moment with 2 time derivatives divided by r. And we got that out in order of magnitude without, by using only, well, we had to use mass and momentum conservation in order to, or energy and momentum conservation in order to decide that the leading order piece would be quadrupolar, not monopolar or dipolar. And then we had to use dimensional analysis and basic ideas about multipole expansions. But using things that are all very familiar from electromagnetism and elementary physics, we got this form up to not knowing a numerical coefficient or precisely what piece of the quadrupole moment is involved. And what we have now derived is a formula that says the precise statement is there's a factor of 4 out in front, which we couldn't get by the simple arguments at the beginning of the class. Here are the same 2 time derivatives that we got by dimensional analysis arguments. It's indeed the quadrupole moment at the retarded time. That's natural to expect. And you pull out the transverse traceless piece, which is not something that we could get by the arguments I gave you at the beginning of the class, of the course. This formula is the simplest formula for computing gravitational waves, and it has the beautiful property that when we brought it into this form, then in the problem that we have up here, the stress in the rod contributes negligibly because the quadrupole moment is the basic thing, or the second moment of the mass distribution, so it's really mass that's doing it. And the tiny pressures, P is small compared to rho, the tiny pressures inside here are negligible contributors to this mass quadrupole moment in a nearly Newtonian situation. And so we no longer have to be concerned about the contribution from the internal stresses. We need to be concerned about only the mass contributes in this formula, not the stresses. Now, if our source were a different kind of a source, if our source were, for example, an electromagnetic field, a very strong electromagnetic field, say inside a condenser, or just a very intense electromagnetic radiation, then it would no longer be true that mass densities were small compared to stresses. Also, the slow motion approximation might well break down, and you would be driven back to this kind of a formula to work with to compute the gravitational waves. But in this situation where the stresses are small in magnitude compared to mass densities, if we use that formula, we just don't need to worry about the stresses. Okay, now I'm going to tell you what happens when you have significant self-gravity. I'm not going to actually go through the details. You'll find them in textbooks. And in fact, the argument I'm going to give you is in Landau and Lifshitz' Classical Theory of Fields, which was written in 1942. During the period between about 1935 and about 1980, there was enormous controversy over whether the formula that I'm going to write down is true. But if you go read Landau and Lifshitz and you understand what they say, their derivation, as far as I can tell, is impeccable and correct. But this enormous controversy that raged, in fact, in the West and did not rage in the old Soviet Union, where everybody understood what Landau and Lifshitz were saying. This enormous controversy generated enormous entropy. And in fact, half of Dan Kennefick's PhD thesis here at Caltech was about this enormous controversy.
It's a historical phenomenon.
It's a historical phenomenon and sociological phenomenon. Okay, historical and sociological phenomenon. And so also to put this in historical context, the argument that I'm going to sort of sketch for you, and that is in Landau and Lifshitz, the reason that people in the West didn't really understand it clearly and follow it is because Yevgeny Lifshitz, who wrote these books, Landau never wrote anything. Lifshitz ghost wrote everything for Landau, at least after the first few years of Landau's life. Yevgeny always insisted on writing things tersely. You may have noticed if you ever tried to read the Landau-Lifshitz textbooks. So to the point that if you sort of know a subject, those are wonderful textbooks. You can learn ever so much more if you already have your feet under yourself in a subject. But if you're coming in cold, they're very hard to understand. And so that has been a source of a large amount of failure of people in the West to appreciate a few pieces of physics that the Russians thoroughly understood in that era, which was an era when there was rather little communication across the Iron Curtain. Okay. I should say I know all these things because beginning in about 1968, I started spending about 6 weeks every other year in Moscow and was close friends with Lifshitz and a lot of the other Russian physicists. And I sort of saw the differences in how people thought on the two sides of the Iron Curtain. Okay, so what is the basic argument? The basic argument is, I'm just going to tell you how it goes, that for systems with, so if self-gravity is important, if it's a significant contributor inside the source to the things that, say, in this case, would hold these masses in motion. So, for example, if these were a binary star system, and gravitational forces were the things that were holding these objects so they didn't fly apart. Then, first of all, it's possible to write the law of energy momentum conservation in a carefully chosen kind of coordinate system. It's having the form T alpha beta plus something, let me call it tau alpha beta. This is an effective, or it's often called a stress energy pseudotensor for the gravitational field. It's not a real tensor because to even talk about it and use it, you have to introduce a special coordinate system. Okay, so in an especially chosen coordinate system, the laws of energy and momentum conservation can be written in this form. Or sometimes they're written, one defines this tau alpha beta in such a way that this is written as minus g, where this is the determinative components of the metric, times T alpha beta plus tau alpha beta, comma beta equals 0. And so there, in fact, in MTW, for example, there's a detailed discussion of this fact. Okay. So energy momentum conservation can be written by the same mathematics as we used before in a coordinate system that is not globally Lorentz by any means, but the coordinate system has been adjusted so that the mathematics of energy and momentum conservation can be written in a form involving partial derivatives, as though it were locally Lorentz. Okay. So this is just a mathematical fact, which Landau and Lifshitz demonstrate and then make use of. The second mathematical fact is that you can go through the same analysis as I went through here, working from the Einstein field equations, including internal stresses, and get the same formula as I have here, but where TJK is replaced by TJK plus this effective pseudotensor for the gravitational contribution. So that HJK, then transverse traceless, T and X is equal to 4 times an integral of TJK plus tau JK over X minus X prime. This is evaluated at the retarded location, D3X prime. And so and then take the transverse traceless part. And once you have this mathematical formula valid in that very special coordinate system, or it's actually a class of coordinate systems in curved space-time, it's still weakly curved. Well, strictly speaking, in fact, what's really required is just slow motion approximation. If you look at it very carefully and deeply, though Landau and Lifshitz don't really make that clear. So what you really need is slow motion approximation, but when people really do this carefully, normally they do slow motion approximation and weak gravity, but still significant in terms of determining the motions of the sources. Once you have these two formulas, the mathematics is identically the same as I just went through. And you wind up in the end then with this same final result, that HJK transverse traceless is 4 over r second time derivative of the quadrupole moment.